So far, we have mostly been talking about the motion of an object along a straight line or on a parabolic path. However, rotational motion, which is the motion of an object as it moves around a circular path, is going to have a lot of the same ideas and conservation laws that we saw when we were talking about linear momentum and energy. It's just that it's going to have new quantities that have different names, but are very analogous to the properties of the momentum and the energy that we were already talking about. Tangential and rotational speed are related, as tangential speed is the linear speed of an object that's rotating around in a circle, and it is dependent on the distance from the axis of rotation. So somebody twice as far away from the center of the merry-go-round will be moving twice as quickly. V, the tangential speed, is equal to r, the radial distance, times omega, which is the rotational speed. Rotational speed is related to the number of revolutions that an object makes when going around in a circle. If you have a record player, then 33 rounds per minute is generally the amount of rotational speed that a record will have, and it counts the number of times that it goes around in a circle per minute, which can be converted into radians per second, which is the general SI unit that we're going to use for V equals omega R. Again, if you have two ladybugs on a record and one is twice as far away, then they will have the same rotational speed. The record will be rotating the same number of times per second. It's just that they will have different tangential or linear speeds. As the farther out you are, the more distance you're going to be covering in the same amount of time. Rotational inertia is our first point of comparison between these rotational ideals and our linear ideals, which we've already established. So similarly to how it is difficult to move an object which has high inertia, which means mass again, linearly, it is difficult to rotate an object with high rotational inertia. So the farther a mass is from the axis of rotation, the harder it is to rotate, the more rotational inertia it has. Rotational inertia is also called the moment of inertia. And as you can see here, it depends both on the shape and distribution of mass through an object, as well as the position of the axis where you're rotating. So a stick that is rotated about one end is going to have more rotational inertia or a higher moment of inertia than a stick that's rotated around its center of gravity or around the center of the stick, because there is more mass farther away when you have the stick rotating about the end than when you have the stick rotating about the center of mass. Our second point of comparison is torque, which is the equivalent of force and is equal to the lever arm times the force. So only the section of the lever arm that's perpendicular to force, or a force that's perpendicular to the lever arm, is counted when you're calculating torque. In our first example here, we have force not being applied perpendicularly to the lever arm, where the lever arm is the wrench. And because of that, we're going to see that it's not going to have as much torque. It's not going to have the same ability to change the rotation of the object as if you were applying a force perpendicular to the lever arm. Instead, if you have more torque and you have the lever arm and the force making a 90-degree angle, being perpendicular to each other, then that's going to have more torque. And if you have a longer lever arm and the force perpendicular to the lever arm, then that's going to be even more torque. When doing these sorts of problems, it can seem like we're throwing out all of our linear momentum, energy, and motion knowledge, when really that is all still true. It's just that it only acts on the center of mass / gravity. The center of mass is the average value of the center of mass is the average location of mass / the average point where gravity is going to pull down on, which is why it's sometimes called the center of gravity. When you look at these two examples, the first one, you're going to see a ball moving in a simple parabolic arc, which is not rotating and has a simple center of mass. However, if you look at the second example, you see somebody throwing a baseball bat and the baseball bat rotating. However, the center of mass of the baseball bat still follows that parabolic arc. The parabolic arc is going to be the arc of any object thrown in a gravitational field which is constant and pointing downwards. And it describes the motion of the center of gravity. So while the bat is swinging around and looks like it's moving up and down and looks like it's having a more complicated arc, in reality, if you look at the center of gravity or the center of mass, it is going to be the same parabolic arc that you see for the more simple baseball. You throw the wrench across the room, before it has the chance to move down, you'll see that the center of mass, while the wrench is rotating, is going to be going at a constant speed across the room. Each of these dots indicates the center of mass, and you'll see that the center of mass is going in a straight line across the room, despite the fact that the wrench is rotating while it does so. The center of gravity also tells us how stable an object is, because gravity is going to be acting along the center of mass. It's going to be pulling down on average through the center of mass. As you tilt an object to the right, as long as the center of mass is to the left of the point of that you're tilting, then the torque caused by gravity is going to be pulling it back down to where it was. Once you pass the point where the center of mass is to the right of the point where you're rotating the object, you will see that the object will fall over because the torque is going to be pulling it to the right instead of to the left, and it's not going to be in a stable position anymore. Because of the way the masses are arranged, you'll see that a skinny cylinder is less stable than a wide cylinder, which is less stable than a cone. Having talked about torque, the equivalent of force which causes there to be an angular acceleration rather than a linear acceleration, we're going to talk about a conserved quantity, which is angular momentum, which is rotational inertia times rotational velocity. L, which is the symbol for angular momentum, is equal to I, the symbol for rotational inertia, times omega, the symbol for rotational velocity. It is also equal to R times P in the same way that torque is equal to R times F. So because of this, angular momentum is a conserved quantity as long as there is no external torque being applied, in the same way that momentum is a conserved quantity as long as there is no force being applied. Angular momentum is also very useful because a lot of forces will act directly between the center of one object to the center of the other object. This means that if the center of one object is where the other object is rotating around, then there is no torque applied, which means that angular momentum is conserved. Even as a comet goes about an elliptical orbit, which remember is a stretched out circle, as r goes up, the distance from the sun goes up, v goes down, and angular momentum is conserved, so we can do calculations based on angular momentum. This is also one of Kepler's laws, which we are going to get to in the chapters coming up. As you can see, there are a lot of equivalencies between linear and angular quantity. Position goes to angle, speed goes to angular speed, acceleration goes to angular acceleration, force goes to torque, momentum goes to angular momentum, F equals ma goes to torque equals I alpha, P equals mv goes to L equals I omega, force equals the change in momentum over time goes to torque equals the change in angular momentum over time, and kinetic energy equals 1/2 mv squared goes to kinetic energy equals 1/2 I omega squared. All of the rules we've been talking about are going to be very similar to what we've seen with rotational objects. All of the rules we've been talking about are going to be very similar to what we've seen with rotational objects. It's just that we need to swap out these variables with variables which are related to rotational motion rather than linear motion. Centripetal motion is circular motion, and centripetal means center-seeking motion and is a set of circumstances which causes circular motion. If speed is constant, all acceleration must be perpendicular to the velocity. In order to bend inward and not outward, it must be pointing inwards in the direction of a circle. In order for this to happen, A is equal to V squared over R must be true, meaning that MA is equal to MV squared over R for whatever force is pulling on it. This being true is what causes there to be centripetal motion, whereas centrifugal force is an apparent force which is caused by you already being in a system which has rotation. Centrifugal force is an apparent force due to the fact that the acceleration inside a rotating system is equal to the apparent acceleration, the Coriolis acceleration, which is responsible for the curl of hurricanes on Earth, and an inward pointing centrifugal acceleration. M times the total acceleration would be equal to the actual forces acting on an object. However, since there are these different types of acceleration, the apparent acceleration, and then the Coriolis acceleration and the centrifugal acceleration, M times the apparent acceleration is going to look like the actual forces minus Coriolis forces minus centrifugal forces. So when you look at the apparent acceleration of something, it is going to look like something is pulling you outwards because you're going in the opposite direction of the centrifugal acceleration. To explain this, I came up with an analog based on the apparent velocity. So with a rotating system, the total velocity is equal to the apparent velocity, how fast you're moving in the rotating system, plus omega to r, which is caused by there being a rotation in the same way that Coriolis and centrifugal accelerations are caused by there being a rotation. So if you have something dependent on velocity, such as wind drag forces, when you look at the forces, it will be as though they are proportional to your velocity plus omega r. Centrifugal force is also useful for simulating gravity. In this example, we have two ladybugs which are inside of a bike tire, which is spinning. Because it is spinning, there is a centrifugal acceleration which is going to act like the acceleration due to gravity and pull them to the edge of the bike tire. Even though it's a fictitious force, it is a real acceleration and is why the International Space Station is spinning on an axis in order to cause this simulated gravity.